Observations from NASA's MAVEN spacecraft reveal that the solar wind causes unexpected interactions with the red planet's weak magnetism. New results from NASA's MAVEN mission reveals that three kinds of magnetic field lines occur at Mars: those draped across the planet by the solar wind yellow, closed lines created by pockets of crustal magnetism blue, and open field lines red created when the first two connect on the planet's day side. A Neil Rao Univ of Colorado MAVEN NASA GSFC Pity Poor Little Mars. It's bigger than Mercury, yet planetary scientists struggle to understand why it didn't end up larger than it is. In its infancy, the red planet must have been an exciting place, with a sizable magnetic field, a much denser atmosphere, and liquid water gushing across its surface. But the magnetic field mysteriously collapsed, most of the atmosphere and water escaped to space, and the surface went into deep freeze. These consequences are likely interrelated, and to help researchers puzzle things out, NASA dispatched the MAVEN orbiter, short for Mars Atmosphere and Volatile Evolution, 4 years ago. Since arriving at Mars in September 2014, its spectrometers and detectors for fields and charged particles have been gathering observations that bear on how Mars lost its atmosphere. Because Mars lacks a global magnetic field, researchers thought field lines embedded in the solar wind would simply drape across Mars as they slid by. This forced intimacy would cause some loss of atmospheric gas through multiple effects that would target both neutral atoms and ions. A computer model of Mars shows how magnetized regions of the planet's crust create bubbles of magnetic field that extend into the atmosphere and beyond. David Brain Univ of Colorado. But right now the calculated leakage is so slow that over 3.5 billion years the planet would have lost the equivalent of a global layer of water 3 meters 10 feet deep and just 1 millibar of CO2, a tiny fraction of what the planet once had. Clearly, the loss rate must have been more vigorous in the past than it is now. Mars isn't completely devoid of magnetism. The loss of its global field billions of years ago, likely because its molten core solidified, left behind localized pockets of remanent magnetism frozen into the Martian crust. These create bubble-like minimagnetar that extend upward from the surface for hundreds of kilometers through the atmosphere and into space. MAVEN scientists were eager to learn just how these magnetized pockets interact with the sun's magnetic field that's carried outward through interplanetary space by the high-speed solar wind. Mission results announced at a recent science meeting in Provo, Utah, show that the planet's interaction with the solar wind is more complicated than thought. Gina DiBraccio, MAVEN's project scientist at NASA's Goddard Space Flight Center, explains that field lines from the localized magnetism can connect with the solar wind's field on the planet's day side, where the solar wind penetrates deepest. Researchers now realize that magnetic field lines carried outward from the sun by the solar wind yellow can encounter field lines associated with pockets of magnetized Martian crust blue and reconnect with one another. As the solar wind moves past the planet toward right, the resulting open field lines red can easily allow atmospheric ions to escape to space. Tristan Weber Univ of Colorado. Once these connections swing around to the night side, they provide a direct escape route for ions from the atmosphere through the cone-shaped magnetotail that extends far behind the planet. What we're finding with MAVEN, she explains, is that a majority of the field lines in the magnetotail are open to space. How much more gas might have escaped over time via this mechanism isn't yet clear. Moreover, the spacecraft found that the collective orientation of field lines within the magnetotail display an unexpected twist. Computer simulations by Ying-Juan Ma University of California, Los Angeles can reproduce this observed twist, but only if abundant magnetic reconnection events are occurring on the day side between the bubble-shaped localized fields and the solar wind field. MAVEN data reveal a twist in field line orientations in the Martian magnetotail. Based on computer models left-center, this argues that reconnection occurs between solar wind and localized Martian magnetic fields. Left-center Gina DiBraccio right, Ying-Juan Ma. Meanwhile, all this reconnection serves to erode the ability of the localized remanent magnetism to fend off solar storms and other charged particle assaults from deep space. And that's not good news for those who had hoped that these magnetized pockets might be good places to search for evidence of past or current primitive life forms on the planet's surface.